Chapter 8, Internal Flow Convection, combined with partial Chapter 11 on cross-flow heat exchanger. Topic 1, the uniqueness of internal flow convection. We have studied external flow convection in Chapter 7. Therefore, we want to first compare these two flow convections. A. What are the differences between internal and external flow convection? The first difference is that external flow convection is between the solid surface and the moving fluid around it, but internal flow convection is between the inner solid surface of the tube and the moving fluid bounded by it. The second difference is that the external flow temperature T infinity is constant and it is a fixed value. However, in the internal flow temperature Tm is not a constant and it changes from the temperature at the inlet to the temperature at the outlet of the tube. The third difference is that the characteristic length LC for external flow convection over a plate is using lengths X or L, but the characteristic length LC for internal flow convection in a circular tube is using the diameter D. As a result, in the definition of local Newton number, the averaged Newton number, and the Reynolds number, the characteristic lengths is all using diameter D for internal flow convection in a circular tube. The fourth difference is in the critical Reynolds number value. For external flow convection, it is 500,000. For internal flow convection, it is 2,300. Therefore, when you try to determine on whether the flow is laminar or turbulent, you have to use this critical Reynolds number for internal flow convection in a circular tube. The last difference between internal and external flow convection is that A. The local heat transfer coefficient H for external flow convection over a slender body is decreasing first, then jumping to a large value, and then decreasing again for a laminar transition and then turbulent flow pattern along the length of the slender body. The local heat transfer coefficient H for internal flow in a tube is decreasing first, and then it remains constant along the length of the tube for both laminar and turbulent flows. B. The averaged heat transfer coefficient H bar for external flow convection over a slender body is defined as the summation of local heat transfer coefficient time the local small area divided by the slender body surface area WL. The averaged heat transfer coefficient H bar for internal flow convection in a tube is defined as the summation of local heat transfer coefficient time the small local inner surface area then divided by the inner surface area of the tube pi dl. B. What are the similarities between internal and external flow convection? The similarity is that both convections can have either constant surface temperature boundary condition or constant heat flux on the solid surface as thermal boundary condition. For a combined internal flow and external flow, which represents the cross-flow heat exchanger, the thermal boundary condition is constant incoming flow temperature T infinity. C. What is the uniqueness of the internal flow convection? The first unique feature is that both flow and temperature field inside the tube are divided into two regions, the entrance region and the fully developed region. In the entrance region, boundary layers developed and merge at the center of the tube. The entrance length measured from the beginning to the merging point is represented by XFDT for temperature field. The entrance length measured from the start to the merging point is represented by XFDH for velocity field. In the fully developed region, the velocity profile remains unchanged along the flow direction. The local heat transfer coefficient is also remaining unchanged along the flow direction. This can be seen in this plot for local heat transfer coefficient distribution along the tube lengths. In the entrance region, the local heat transfer coefficient is decreasing. Then in the fully developed region, the local heat transfer coefficient remains unchanged. Since the local Newton number is defined as local heat transfer coefficient times diameter divided by the fluid thermal conductivity, in the fully developed region, all these three are constant. Therefore, the local Newton number is constant in the fully developed region as well. At this point, it is clear to study internal flow convection, we want to know where the fully developed region starts. How to determine it? For our temperature field, equation 1 defines the entrance lengths XFDT for laminar flow, which is 0.05 times Reynolds number times Prandtl number times diameter. Equation 2 defines the entrance lengths for turbulent flow. For velocity field, equation 3 defines the entrance lengths XFDH for laminar flow, which is 0.05 times Reynolds number times the diameter. Equation 4 defines the entrance lengths for turbulent flow. The second unique feature is that the tube can be long or short. This is a short tube with length L1 and a diameter D. This is a long tube with diameter D and length L. Both have the same entrance lengths. This is the local heat transfer distribution over the lengths for a short tube. You can imagine the averaged heat transfer coefficient over the short tube lengths is not same as the local heat transfer coefficient in the fully developed region. However, this is the heat transfer coefficient distribution for long tube. Since the contribution and influence on the average heat transfer coefficient from the entrance region is so small that the average heat transfer coefficient over the whole length is close to the heat transfer coefficient in the fully developed region, which is a constant. Now we can draw the conclusion. For a long tube, the entrance effect on the average heat transfer coefficient for the tube can be neglected. As a result, the average heat transfer coefficient is approximated by the local heat transfer coefficient in the fully developed region, which is a constant. Similarly, the average Newton number is approximated by the local Newton number in the fully developed region, which is a constant as well. At this point, to study convection, you want to know whether the tube it is long or short. How to determine? For laminar flow, it is long tube if the length of a tube over the diameter of a tube is greater than a combination of constant 0.125 times Reynolds number times Prandtl number. Otherwise, it is short tube. For turbulent flow, it is a long tube if L over D is greater than 60. Otherwise, it is short tube. At this point, we covered topic 1, the uniqueness of internal flow convection. It includes the differences and similarity between internal and external flow convection, as well as the unique features of internal flow convection. Next, let's practice on selecting proper equation for fundamental variables. D. Example 8-1. For an engine oil at 400 Kelvin flowing in a tube with a diameter d 0.02 meter, a length L 12 meter, and a flow rate m dot 0.0052 kilogram per second, we need to determine 1. The mean velocity of the flow, 2. Reynolds number and the flow pattern, 3. Velocity and thermal entrance lengths, 4. Determine whether it is long tube or short tube. Engine oil property is provided here. Equation 1 defines the mean velocity of internal flow. Plug into number, mass flow rate, density, cross-section area of the tube. We get the mean velocity of the flow. Equation 2 defines the Reynolds number. If we plug UM, the mean velocity, and the cross-section area AC into the definition of a Reynolds number, we yield a new equation for the Reynolds number. Then plug into numbers, mass flow rate, pi, diameter, viscosity. We get a small value of Reynolds number compared with the critical one, and we decided it is a laminar flow. Equation 3a defines entrance lengths for the velocity field XFDH. Plug into numbers, 0.05 times Reynolds number times diameter. Then we get a small value of entrance lengths for the velocity field. Equation 3b defines the entrance lengths for the temperature field XFDT. Plug into numbers, 0.05 times Reynolds number times diameter times Prandtls number. Then we get a big value of entrance lengths for temperature field. Finally, since the flow is laminar, we compare lengths over diameter with a combination of parameters. We plug into the number into the combination parameters. We get 716.3. Then 1 over d, we get 600. Compare these two numbers, we decided it is a short tube. Bonus practice. Can you sketch both velocity and thermal boundary layers inside the tube? See you next time.